do a second frequency analysis class exercise that is basically based on the code you turned in or should have turned in for CP7, which was that FFT-based graphic equalizer. So I posted CE8 just a little while ago. I don't know if you've seen it yet or not, but it's up there. And for this exercise, you're going to build on a reference implementation of the graphic equalizer, the FFT-based graphic equalizer. So we're going to give you basically the sketch code to get you going, which implements that graphic equalizer and the biquad filters that you can switch in and out. So low pass, high pass, band pass filters. And what you're going to add to the sketch is some more frequency analysis based visualizations. So one thing you're going to do, first thing you're going to do is write some code to detect the strongest frequency in the input signal, whether it's a sample player like a music sample or microphone input, and display that in the graphic equalizer. And I've got some, also in this sample sketch, I've got the beginning of that, basically the code to visualize the strongest or frequency. And by that, what we mean is the FFT bin, which has the highest power at any one moment, and render it in a different color. And basically, the example renders that as a red bar. So it'll show you what the peak or strongest frequency is at any moment in time. So that's one task. And if you take a look at the sonifying processing with beads tutorial documentation, which is also on Canvas, there is example code which does what you need to do for analyzing the FFT frequency spectrum data and finding the strongest or most highest power frequency. And this code right here, it's listing 9.2, does that. So if you look through here, this should basically tell you what you need to do for this first part of the assignment. So it should look very familiar. It's the same kind of setup. You're using the same set of UGens to do FFT analysis. So the short frame segmenter and the FFT and power spectrum UGens. And the interesting part of this example is, I'm sorry, that 9.2 is actually just a basic graphic equalizer. I think it's 9.3 does the additional analysis where you pull out the strongest frequency. Yeah, this is it. So if you look at 9.3, and especially the main draw loop, where it computes a mean frequency, so it's a running average of the strongest detected frequency. And this calculation is only being done for frequencies less than, it's a constant here, but 3,000 hertz. And the reasoning for that is that, especially for vocal sounds or musical sound inputs, there's often a lot of high frequency information in the signal, which could cause this very simple algorithm to jump wildly back and forth between a lower detected strong frequency and some transient or like a drum beat or a cymbal hit, something like that. A lot of transient, very strong frequencies. So basically, this is kind of a fudge here, or a hack, where we're only going to pay attention to frequencies below some cutoff, say 3,000 hertz in this case, and detect the strongest frequency at less than 3,000 hertz, so you don't get this very noisy visualization. So that's the reason for that if statement here. So, let me first show you the sketch that you guys will get, and then I'll show you kind of a more or less working implementation of that strongest frequency detector visualization. So this should look familiar. Basically, this is just the FFT-based graphic equalizer display that you guys did for CE7. And you'll see a red bar here. It's not actually moving right now. And the reason is it's just stuck at a default 400 hertz. And if you look in the code, you'll see that. What you're going to do is actually calculate what this strongest frequency is. And this red bar will start moving around with the detected frequency. And all the filters are still in place, so you can do low pass filtering, high pass filtering, or band pass filtering. Toggle the mic on and off. These two controls are not wired up. There's no, so these are, I just put these in the sketch, but there are basically blank or stub handlers for them. So what this is intended to do is the next step, or one of the next steps in this project, which is once you've detected the strongest frequency in the input signal, we're going to ask you to do a very simple sine wave based resynthesis of that detected frequency. And so what that means is, let's say in your input song or mic input, your detected strongest frequency is 1200, or about 1200 hertz, let's say 1205 hertz, something like that. What you're going to do for this resynthesis task is create a wave player, and it will play just a simple sine wave at that detected frequency. And those controls there just turn on and off that feature. So if I click resynth, the resynth toggle button, what we want you to do is start playing that wave player at the detected frequency. And then this slider can change a gain control to mix that in or lower the volume of that resynthesized sine wave.
So is that in addition to what's currently playing, or
Yes. So you can play it in addition to what is currently playing at either a sound player or the live mic input. So I'll show you an example of what that looks like and what that sounds like. So, first of all, this is actually a working version where the frequency detected is changing. So the strongest frequency is being detected, and you can see the red bar moving around. Now it's on the left side, mostly on the left side of the display, because the strongest frequency is pretty low. It bounces around between like 250 hertz up to maybe 12 or 1500 hertz with this particular sample. And you can low pass filter it, and it's still working. You high pass filter, and you should see that the detected frequency jumps up a little higher. There's still, it's only ever going to be up to 3000 hertz or 3K hertz, because there's that if statement in there where we only detect frequencies below that limit. Okay, so now if I toggle on the microphone and the reset, may get some feedback. It works pretty well for whistling, or if you have a good singing voice, a stable singing voice. And what this is doing is it's playing back a wave file. Let me make it a little louder. Let me see the wave player. So it's pretty well matching the fundamental tone of my whistle. Okay. And that's a good way to debug it, is this re-synthesized wave player and toggling the mic on and then whistling. You can really hear that sine wave is pretty well matching with the tone of your whistle or your voice. That kind of just is a good sanity check that the detected strongest frequency is correct. Question?
This should work with both the wave file and the mic input?
Yes, however, some wave file, because of the way that this strongest frequency detection works, there is quite a bit of lag between, there's a buffer that has to be examined a time buffer that has to be examined to figure out what the strongest frequency is. And there's a lot of lag. And so if your music is changing rapidly in frequency response, that detected frequency will be just very noisy. So it does much better on like more constant tones like whistling or singing slowly. I've got an example wave file where, and the other problem with the microphone input is you can easily get feedback. So if you're playing back over the speakers, the microphone is going to pick up what is being played back, and you'll get like a feedback loop in certain cases. But if I play back a wave file of my recorded whistle instead, it works pretty well. Sorry. I was playing back the example file. Yeah.
What frequency is the strongest? No, you can do that.
You hear that generated sine wave kind of following the detected strongest frequency in that sample.
And then I guess you'd be updating it as this goes.
Okay, so in the sample sketch, there's a few different sample wave files. One is that whistle, there's the techno song, there's that accordion song, the Star Wars theme, or you can use your own wave file to test with, and please turn it in if you use one of your own. Okay. So any questions about those two tests? So that's doing the strongest frequency detection and visualization, and then a very simple resynthesis of that detected frequency. Okay. The next thing you're going to do is use the peak detector UGen. So it's another frequency-based analysis tool to implement another very simple beat detector. And now, this one's going to work really well for like song segments that have like a strong drum beat to them. So there's a drum loop wave file in the data folder also that you can use to test this with. And so this is going to be just simple beat detection and visualization. And in the example in the sonifying processing PDF that's online, you can find some code for doing this very simple beat detection. It uses the same FFT and short frame segmenter and power spectrum UGens wired up the same way basically, but you're also going to use this peak detector UGen and there's a couple different parameters that can be set to fine tune what type of beats it detects and what threshold of the transient sound that those kind of drum beats or whatever it is have to reach before the beat is detected. And then in the rendering loop, the draw loop, and I'll show this working example. What this is going to do is it's going to display a circle on the screen, and it will flash in time to the detected beats. So what we're asking you to do is basically fold this code into the main sketch and be able to detect or display any detected beat in your input signal along with the FFT equalizer and the strongest frequency, and just basically show all that together on one sketch. So let me show you what that looks like, just the beat detection alone. So take a look at this code in the Sonifying Bees with Processing book on Canvas, and take a look at this particular example here. It's noted in the assignment. It is 9.4, this code listing, and it's pretty simple. Basically, the only thing you're really adding to the sketch code that we're giving you is this peak detector UGen and wiring it into your graph. And then you can have some kind of other visualization, but you could just use this where you're drawing ellipse and you're changing the brightness of the ellipse to indicate when detected beats happen, and just draw it on top of, maybe to the right of your frequency histogram, or the graphic equalizer, the FFT graphic equalizer. So you do all that, then that's worth 100 points. So it's doing the strongest frequency detection and visualization, the simple resynthesis with just a sine wave, a wave player, the peak detector-based beat detection and visualization, and I think that's it. Any questions about that? All right, so from here on out, why don't Ben and I either go around or have you all come up if anybody has code they'd like us to look at or any questions